in April, there was a hackathon at the IBM Canada Labs where the challenge was to write an IBM Bluemix application that uses the Watson Insights for Weather service to get weather information. We got a team together and we brainstormed a few ideas, and we decided that we wanted to use a Raspberry Pi with Quarks running on it to represent an edge device. And we also wanted to include the Bluemix streaming analytics service to perform some real-time analytics. This was obviously above and beyond what the original challenge called for, but we had lofty goals, and we knew that with the portfolio of products and services that we were familiar with, it should be fairly easy to achieve our goals. So we eventually decided on a water conservation project where our mission became to save the world one smart sprinkler at a time. So now, how often have we seen this? This is not smart, but it happens a lot. And there are drought conditions in many parts of the world, including California and the US, where water shortage is a real issue. The government in the affected areas are trying to conserve water by imposing bans or restrictions, but it is often difficult to enforce the bans effectively. And some people are simply rich enough or ignorant enough to ignore the bans. Freshwater crisis is a looming problem in many parts of the world, and irrigation for agriculture is a major contributing factor. Here are just two examples. The Aral Sea in Central Asia is almost dry, and the Colorado River in the US is dying. A majority of the water drained from these resources was used for agriculture, for irrigation. And if you do a quick search on the internet, you will see many more other scary examples of water crisis similar to this, all in different parts of the world. So we need to conserve water and be smart about how we use water. Having smarter sprinklers will help to conserve water, not only in the urban areas, but especially for agricultural irrigation. There are smart sprinklers out there already, but they are not smart enough. We need smart connected sprinklers that are smart enough to perform local analytics to determine whether the local conditions require the sprinklers to be turned on, and something that can also connect to a backend system for more in-depth analysis. For example, to check for rain in the forecast and or government bans on water usage. Now, I'm not only talking about the sprinklers in the urban areas. We are also talking about those hundreds and thousands of sprinklers on huge commercial farms. Like farms across the US spend hundreds and thousands of dollars for irrigation, for watering their lands. Having smarter sprinklers will help to not only conserve water, but also protect the bottom lines for farmers. So it's a win-win situation for everybody. So we set about building a prototype of our smart sprinkler using a Raspberry Pi. And I'll now hand it over to Kendrick to show you what we built. And then following the demo, we will show you how we built the prototype.
Thank you, Mary. So in front of you, you will see the brain of our smart sprinkler system. This is the Raspberry Pi. It's got three main components. Obviously, there's the moisture sensor currently in the water right now. There's the sprinkler control. For this demo, the sprinkler control has been replaced with an audible buzzer. So when it turns on, you will be able to hear it. The CPU itself is running Quarks and is connected to the Watson IoT platform via the Ethernet cable. An average smart sprinkler may be able to control sprinkler based on the moisture level of the soil. But this sprinkler that we have here is much more smarter than that. Whenever the Pi thinks that it should turn on the sprinkler, it will first send a water request to the IoT platform. Then the Streams application will run a series of analytics and provide guidance back to the sprinkler. When it comes to the type of analytics that the Stream application can perform, the possibilities are endless. But for this demo, we're going to show how it's using the weather forecast and governance data to make decisions for the sprinkler device. And we need a way to show what the Pi is thinking. So for that, we have a web dashboard application. And the sprinkler device is going to send a status to the web UI. And here, the web UI is divided into two parts. Well, on the lower part is where the sprinkler status is being shown. The blue gauge on the left shows the current moisture sensor reading. In the graph, there's two main lines, a red line and a green line representing the moisture threshold for turning on the sprinkler on and off. When a water request is made, you will actually see a dot on the running blue line. You don't see it now, but during the demo, you will see that. And there's also an indication when the sprinkler is on, represented by orange dot on the blue line. On the upper half of this UI, you will see a weather forecast. That's the weather forecast for the sprinkler location. For the purpose of demo, we need a way to simulate the data, or the weather data. So there's this weather simulation which we can turn on to control whether the forecast should be sunny or rainy. You may also notice this water band button just underneath. We will use that to indicate if there is a water band in effect. So for the first scenario, we are going to simulate the weather data so that it's going to forecast sunny condition. Water band is off at the current moment. So once I take the sensor out of the water, you will see moisture level starting to drop until it hit the lower threshold, at which time a water request will be sent. And because there's no rain in the forecast, we are expecting the sprinkler to turn on, and you should hear an audible buzzer. So I'm taking out the sensor from the water now. As you notice on the graph, the moisture level is slowly dropping because it's losing moisture. And once it hits the red line, we will see a green dot indicating a water request. In this case, because there's no rain coming, you now hear the buzz indicating that the sprinkler system is on. This sprinkler is going to turn on until the water level hits the upper threshold, and then it's going to turn off by itself. In the next scenario, we're going to show that what would happen if there's rain in the forecast. Obviously, for a smart sprinkler, we don't want the sprinkler to turn on when there's rain, and we're going to show that. So once again, I'm going to put the water sensor out of the water. The rain is going to come, but not yet. So the moisture level is going down. And as soon as it hits the lower moisture level, a water request is going to go. But this time, the sprinkler does not turn on because there's rain in the forecast. And as we have this rain simulated data, the moisture level is going to rise up again because it's raining. For the last scenario, I'm going to show how the water band is going to have an effect on real time on the sprinkler. So we're first going to turn the weather simulation to sunny because we do want the sprinkler to try to turn on and moving the water band to on position. I'm going to take the moisture sensor out now. As the moisture lowers, reaching the lower threshold, the sprinkler is going to ask for water request. This time, though, because the water band is on, it's not going to turn on the sprinkler. And you'll see a series of green dots indicating that the sprinkler is asking for water request, but because the water band is on, it's being rejected each time. Now we're going to show how lifting the water band in real time is going to have an effect. So as soon as I lift the band, the buzzer should go off right away. And we're also going to show that we can put the band on right away after that to turn off the sprinkler. So we're going to turn it off. The buzzer goes on, indicating the sprinkler is on. Now we're going to turn it back on, and the sprinkler would go off right away. So that concludes the demo part. If Samantha is going to show how this is implemented inside the Pi.
Thank you, Kendrick. So in the next session of the demo, I'm going to talk about how we have actually implemented this application. So first of all, we're going to show an architecture diagram. So we have the smart sprinkler, which is implemented with Quarks on the Raspberry Pi. This application will do the local analytics and basically continuously monitoring the moisture level in the soil. To talk to the back-end services, we have leveraged a lot of the Bluemix services that are available to us to get us up and running very quickly. So for us to connect and communicate with the back-end services, we are using the Watson IoT Platform, which under the cover is running MQTT for the devices to talk to the back-end services. For back-end analytics and the business decisions on whether we are going to turn on the sprinkler or not, we use the streaming analytics service from IBM, which allow us to do real-time analytics with the data that is coming in and providing a real-time response to the data. For us to get the weather forecast, we use the weather company API, which is Insight for the Weather, which allow us to basically query the weather forecast in the next 7 days so that we can actually make a decision to decide whether we will turn on the sprinkler or not. And then for real visualization and actually looking at the data, we use the Node.js server on Bluemix as well as React.js for our web UI. So in the following so this is all interconnected. And in the following presentation, we are going to focus on two pieces of the application. So we're going to focus on the Quarks application design as well as the back-end streaming analytics application to show you how we actually did the back-end analytics. From the Quarks application point of view, the goal of the application is to do local monitoring of the moisture reading from the soil continuously. And as part of kind of a device, like when you're reading data from the device sensor, one of the problems is that sometimes the reading may not be very accurate. Sometimes you might get a spike. Sometimes you might get a lower reading than normal. So for us to be able to get a more accurate reading, we'll calculate a rolling average of all of the current moisture level using a window of data. And we will not communicate to the backend services unless we have to. So we will only detect, if we detect that the current moisture level is too low, that's when we're going to send requests to the backend system to ask if we can turn on the sprinkler. And then as the last part of it is that the sprinkler would not get turned on unless the backend service has allowed us to turn it on or give us basically permission to turn on the sprinkler. In this diagram here, this is the architecture of the application. So at the core of it is what we call the sprinkler controller. The sprinkler controller simulates the current moisture reading as well as the sprinkler activity, which is the buzzer. For us to talk to the actual sensor on the Pi, we implemented the sprinkler controller using the sprinkler simulator with sensor class, and we go through Pi4j to actually work with each of the sensors that we have or the devices that we have. For the backend services, so all the readings we collect locally, and then for the backend services, we use Quarks to collect this information and send information to the Watson IoT platform. So next, we're going to kind of look at the code and see what we have done. So before we do that, we'll look at the actual physical setup of how we have hooked up the different sensors. So the first sensor that we've hooked up is the moisture sensor. So this is a picture of the moisture sensor. There are three things for you to hook up. So you have to hook up the power to pin 1, which is going to give you a 3-volt power to the sensor. And then we also hooked up it to the ground pin. For us to get the data out of the moisture sensor, you have to hook up the digital output of the sensor to the Pi. And I have hooked it up to pin 11 on the Pi in here. So what it does is, if the moisture is detected to be too low, then the digital output will tell you that the output is actually low from the sensor. And then if the moisture sensor says it's dry, then you'll get a high output from the sensor. The next thing we needed to hook up is the sprinkler or the buzzer. So this is very easy to hook up. So a breadboard here, and I hooked up the input to the buzzer onto pin 13, and then I also hooked it up to the ground pin to pin 6. So that's all there is to it from a circuits perspective. And now we're going to kind of talk about how we actually write the sprinkler controller. So to write the sprinkler controller, I created the sprinkler controller interface. And the job of the sprinkler controller is to gather the moisture reading from the moisture sensor, allowing us to control the buzzer on and off, and also control the rain simulation. For us to be able to get the moisture sensor reading into the Quarks topology, the controller needs to implement the supplier reading API. So it allows us to basically kind of provide a reading into the Quarks topology so that we can analyze it locally. In a lot of the examples that you will have seen in the Quarks community is that the example will show you how to actually create a topology that reads sensor information as primitives, so like double or floats. But on top of that, you can actually use a custom class to provide the sensor reading. So for me, I've created a custom reading class, and the reading class will provide information about the current location of your sprinkler, which is the GPS location, which I've hard-coded here, whether the sprinkler is on and off, and the current moisture level. For us to be able to use it in the Quarks topology, your custom class has to be a serializable object, so I have implemented serializable in the class so that I can pass it into the Quarks topology. So that's all there is to it, to the sprinkler controller interface. So after I've defined the interface, this is the sprinkler simulator with sensor class is the concrete implementation of that interface. So on top of that, we have 3 things in here from this class. So for you to work with a buzzer, you have to create a GPIO pin digital output object. And for you to work with the moisture sensor, you have to have a digital input object. And then for you to actually kind of interface with it, you have to create a GPIO controller, which is a class that is part of the Pi4j library. So before you can work with it, or can basically call it, you have to provision these pins in your controller or in the application. So in the constructor of our sprinkler simulator class, what I have done is I have provisioned the moisture sensor to GPIO 0, and I have provisioned the buzzer to GPIO 2. One thing you will notice is that even though I've wired up the moisture sensor to pin 11 on the Raspberry Pi, when I actually provision it using Pi4j, I have to use a different pin numbering option. And the reason for that is that Pi4j follows an abstract pin number scheme from the Wiring Pi project, which allows the application to be more resilient to any hardware changes. So this is an abstract numbering. And if you look at the Wiring Pi project and how it maps to the Raspberry Pi pin convention, you'll see that pin 11 is actually referred to as GPIO 0 in Pi4j, and pin 13 is referred to as GPIO 2 in Pi4j. So this is why the pin numbering is set up like this here in the code. So now that we have provisioned all our sensors and be able to work with it, we're going to talk about how we actually get the moisture reading from the sensor. So as I have talked about before, in order for us to basically provide data into the Quarks topology, you have to implement the supplier reading interface, which is on the top left corner here. You just have to implement this get interface. And then in this method, we'll get the moisture reading from the sensor and then create a reading object and return it. And that's how you provide data into the Quarks topology. If you look at the get moisture method, this is the actual method that we interface with the moisture sensor to understand what the current moisture level is. So in here, I ask the sensor, is the reading currently low or high? And if the reading is low, then I know that there is enough moisture in the application. That's when I override the simulator to make it to return a really high moisture level. And if it's low, then we'll just kind of use whatever is simulated from the superclass and return that as the current moisture level. Controlling the sprinkler or the buzzer is also very easy. So I have a method that allows us to turn the sprinkler on and off. And so whenever this method gets called, we'll just set the pin state of the buzzer. So if the sprinkler is on, then we'll set the pin state to high, and if the sprinkler is off, we'll set the pin state to low. And that is easy. So now that we have set up the sensor and allow us to be reading from the sensor and controlling the buzzer, how are we going to use it in the Quarks application? So first of all, so this is the application that I have written. So first of all, I have created the smart sprinkler object. So as is in the screen here, I've created the smart sprinkler simulator with sensor object. And then I created the direct provider as well as a topology, as Queenie has shown us before. So you set up the topology for your Quarks application. And then I asked the topology to pull data from the smart sprinkler every second. So basically, whenever the data is pulled from the smart sprinkler, the get method of the sprinkler class get called, and then it will return a reading object from the smart sprinkler. And then that will create a T-stream of reading, which is the current reading of the moisture level. So now that we have the reading, we are going to try to calculate the rolling average of the reading. To calculate the rolling lab average, you have to do two things. The first thing you have to do is you have to set up a window, because data is flowing into the application continuously. So you have to have a window of data where you're calculating the rolling average for. So we created a window data calling the last. So given the T-stream of moisture reading, we call the last method from that T-stream to create a window. And then with that window, so this is a sliding window. So what that means is that we'll keep the last 9 readings in the window. And whenever a new reading comes in, the oldest reading will get discarded. And then also, whenever a new reading comes in, the aggregate method will get called. And at that time, we're going to look at the content of the window and calculate the average moisture reading from the 9 readings that we have in the window. So that is the code that we have done that. As part of this aggregate call, I also use the average reading to kind of decide if we have enough moisture in the soil. And if there's enough moisture in the soil, then I will turn off the sprinkler. And then we created a new reading object with the average reading and then pass it on to the downstream for further analysis. Now, the next thing we have to do is go, okay, now that we have the average reading, we need to decide if the current moisture level is too low. And if it's too low, then we want to send a request to the IoT platform and basically to the backend service to see if we can turn on the sprinkler. So this is the code that does that. So first, we call this filter method. So what is actually saying is that if the current average moisture reading is too low, and the sprinkler is turned off, and we know that there's no rain coming, then I need to basically ask to turn on the sprinkler. So this is the filter method will allow the reading to go through if that condition is true. Once it has gone through, and that means we have to make a request to the backend service to turn on the sprinkler. To do that, we'll create an IoT device, as Queenie has shown us, and I have just hard-coded the device configuration in here. And then because the IoT platform basically require to talk to the IoT platform, it is required that we send in our request as JSON object. So before we make the request, we converted the reading into a JSON object, and then we send, we call this events method from the device to send the water request to the backend. And that's basically the end of that topology flow. So if we go from gathering the moisture sensor information, calculating the rolling average, and then making the request. The next thing we want to do is, okay, now that we have made the request, we need to kind of go, are we really allowed to turn on the sprinkler, and how do we decide that? So the decision to turn on the sprinkler is done by the backend, and for us to actually receive commands from the backend, we call this device.commands method, which is going to get responses back from the streaming analytics service to tell us whether we are allowed to turn on the sprinkler or not. And then for each of the response we get back, we look at the payload of the response and see if we are approved to turn on the sprinkler. And if we're not approved to turn on the sprinkler, what is the reason why we're not approved? And then we react accordingly. So if we're approved, then we just turn on and off the sprinkler based on the response we get back. And then if we know that we are not approved, and we know, and backend, basically the forecast is telling us that it's going to rain, then we just calling the smart sprinkler to schedule rain and make rain in the next 10 seconds. And the last thing you have to do to run this topology is submit it to the direct provider that we have created at the beginning. And then all you have to do with this is that you just follow what Queenie has shown you to export that application into jar file, and then I deploy it onto the Pi as is. So the next thing what we're going to do is Mary is going to take us through on the streaming analytics side to show you what we have done with the backend service.
Okay, can you hear me now? Good. All right, so Samantha showed you how from the Pi we are sending events to the device, and also she's waiting for commands back to indicate whether the sprinkler should turn on or not. We used IBM Streaming. You can't hear me? Sorry, there's technical problems here. Oh, you can hear me? Okay. All right, sorry about that. So we are using the IBM Streaming Analytics service to perform the backend analysis. So Samantha showed you how the Pi sends the event to the IoT Platform service. Now to perform this request, we have a couple of Streams application running in the Streaming Analytics service, which will receive the event, perform the necessary analytics, and then that will decide whether the sprinkler should be turned on or not, and then we send that decision back as a command back again via the IoT Platform service. IBM Streams has a number of toolkits available that makes it easy to write Streams applications, and these toolkits are publicly available for free in the IBM Streams GitHub repository. One such toolkit is the StreamsX IoT toolkit. This toolkit facilitates the writing of Streams application that integrates with the Watson IoT platform. The toolkit provides a pre-built, ready-to-run Streams application that takes care of the connectivity to the Watson IoT platform. The IoT toolkit further provides a publish-subscribe model for independent Streams application to subscribe to device events made available through this IoT connector application that comes with the toolkit. And when the application decides that it needs to send a command back to the device, it uses the same connector application to connect back to the IoT platform service and to send the information back. So what this means is that with the toolkit, it's easy to set up connectivity by running that pre-built application. And once we have that running, all we have to worry about is writing what I keep referring to as an independent Streams application that will do the analytics. And you're not obviously then limited to a single analytics application. You can write as many to do as many analysis as you need to on the device events, on information that's coming from that device. Okay, so let me show you an overview of the Streams application that does the actual analytics. So I'm switching over to Stream Studio, which is so here is Stream Studio, an Eclipse-based development IDE for developing Streams application. I have a couple of projects here containing my Streams applications, and the IDE provides a graphical editor that allows you to construct a streaming application using simple drag and drop. A Streams application is made up of a set of operators that process the data flowing through the application. So the graphical editor provides a palette that contains the operators that you would want to use, that you simply drag and drop it into to create your application. You connect them and you configure the operators to process the data as you wish. And then down here we have what we call an application graph view that allows you to visualize the topology of your applications. So each box here represents an application. And for our prototype, for the Streams application, we actually wrote 3 separate applications that are interconnected. So each box here represents an application. And what you see here is a very typical organization of a streaming application, in that there's usually an ingestion step where you get data into the system, into your application, followed by one or more applications that does the analysis on the data, and then usually followed by a set of applications, or could be in the same application, where you take action based on analysis that you've done on the data. So in our case here, this first application here ingests the device events made available by the IoT connector application that we have running, that provided connectivity to the IoT platform service, where the Pi was sending the sensor information. And then our application, the analytic application here, gets that data provided by, made available by the ingestion application. It does the required analytics, like checking the weather forecast, querying business rules to determine water governance on the water usage, followed by publishing the decision in the form of a command back to the device. So that's the topology of our applications here. Now let's take a closer look at our ingestion app. This application uses an operator provided by the IoT toolkit that I had mentioned earlier to subscribe to device events of interest. So it's a matter of using an operator that the toolkit makes available, and you just configure the operator to say what device events you want to subscribe to. And that makes the device events available to the application, and then we use another operator also offered by the toolkit to extract the application data out of the device event information, and make it then available to the rest of the Streams application using an export operator. If you remember what Samantha had shown, the device event data comes through as in JSON format. So what this extract operator does is it gets the JSON, extract the application data out of it, and convert it into what we call a Streams tuple that can be used by a streaming application. And next here is our analytics application, which does the required analytics on the data that comes from our sensors, from our devices. So this export operator here made the sensor information, device events available to rest of our application. And this is an import operator that connects to that export to get the data flowing through this side of the application. And as you've seen in the demo that Kendrick did, the part of the demo that Kendrick did, we could get real data information from the Watson IoT Watson Insights for Weather API, which would get you the real weather information. Or we also had a weather god to simulate weather, so that we could actually do our demo. So this operator here does a check. That is essentially a router that checks to see which weather information we should be using. And then based on the check, we would either get information from the real weather information from the Watson Insights for Weather API, or get it from the simulated, from the weather god, the simulated weather information. Once we have the weather information, we then pass it along, and further along in our application, we check business rules to see whether there are any bans or water bans in the affected area. And taking all of that information into account, a decision is made, and that decision is then routed to both the UI. So this part here routes the decision to the UI, so we can see the UI getting updated with the decision, and it also routes it to the device through an export. Down here you see a sort of like a standalone operator, and what that operator does is it periodically checks our application to see if there's a water ban. So, and if there is a water ban, it relays that information immediately, and it gets relayed back to our device. So how does that the decision and the water band information get to our device. We have another application here, which takes the information, which connects to our export operator here that contains the decision information. And then we scrub the data and we convert the data, the decision, which is the data, into a JSON format that can be sent back to our device. And the payload in that JSON contains the decision that, sort of the information that our Quarks application is expecting. And then this is another operator that comes with the IoT toolkit that allows you to publish that event or command back through our connector application, which goes through then the IoT platform service to relay it back to our device itself. All right, so and that completes the whole circuit from the Pi generating the event, our Quarks application making that event available through the IoT platform, it coming into the Streams application that makes the decision as to whether the sprinkler can turn on or not, and then the command gets relayed back. So the decision gets relayed back as a command. And if you step back to look at our organization of our application here, what you'll notice is that the ingestion and the command app can stay pretty standard, constant. I mean, as in you just need one application to get the sensor information, and then one application that can publish commands back to the same device. And you can plug in as many analytics application as you want that processes and analyzes the events that's coming from the device. And they can all connect back and send commands back to the device as necessary. And that's just how simple it is. And it's literally plug and play. So, and that is all that I have to show from the Streams application side of things. I will now hand it back to Samantha to wrap up the webcast.
Thank you, Mary. Can you please show the charts?
Okay.
So thank you for everyone for watching. I hope you have enjoyed our demo and our tutorial. Before we end the webcast, here are some resources to help you get started. For information about Apache Quarks, visit our site at quarks.incubator@apache.org. For the material that we have presented today in terms of how to work with sensors on Apache Quarks and connecting to Watson IoT Foundation and also receiving commands, we have created 2 recipes on developer works. So check it out there if you want to start writing your own application. It will give you step-by-step instructions on how to write one of these applications. For more information about IBM Streams and our Bluemix streaming analytics service, here's are the resources to help you get started, which allows you to do real-time analytics for analytics. And last but not least, if you want information about our IoT platform service, here's a link for you to get started on how to work with Internet of Things. And that is the end of our webcast. Thank you very much for watching.